It's hard to talk about the future of technology without hearing the phrase quantum computing. This isn't just a faster version of your current laptop. It's a completely different kind of machine, leveraging bizarre quantum mechanics like superposition to tackle problems previously deemed impossible. But before we imagine a world solved by qubits, it's worth taking a sober look at the incredible opportunities and the serious hurdles ahead. Why all the excitement? The core power of a quantum computer lies in its ability to handle complex calculations that would take classical supercomputers millennia. Academic research highlights 3 major application areas where the quantum advantage is most potent: simulation and discovery, optimization, and machine learning. Quantum computers are naturally suited to simulating quantum systems. This ability is expected to revolutionize drug discovery and materials science. Researchers could model molecular interactions with unprecedented accuracy, leading to the rapid development of new medications, more efficient catalysts, and materials for things like better batteries or solar panels. For problems with a massive number of variables like complex logistics, traffic routing, or financial portfolio management, quantum optimization algorithms can potentially find the best solution exponentially faster than current methods. While still nascent, the potential for using quantum computing to accelerate complex machine learning training and data analysis is significant, especially when dealing with high-dimensional datasets. Despite the immense promise, quantum computing faces 2 major categories of challenges: the technical and the existential. Quantum computers are famously difficult to build. Their fundamental units, qubits, are incredibly sensitive to environmental noise. Even a tiny vibration or temperature fluctuation can cause them to lose their quantum state, an issue known as decoherence. This instability leads to high error rates. Current machines are often described as being in the noisy intermediate scale quantum era, meaning they aren't yet scalable or reliable enough to perform the most complex, world-changing calculations that require millions of fault-tolerant qubits. They are also enormously expensive to build and operate due to the need for highly controlled, often near absolute zero, environments. Perhaps the most pressing risk is the threat to cybersecurity. Today's global financial and communication systems rely on public key encryption that is only secure because classical computers cannot efficiently factor very large numbers. However, the development of Shor's algorithm means that a sufficiently powerful quantum computer could break these cryptographic protocols, compromising confidentiality and integrity across the entire financial system and critical infrastructure. This existential threat means institutions must now race to develop and implement post-quantum cryptography standards before a powerful machine arrives. Quantum computing is not a universal replacement for your current computer. It is a specialist tool designed for specific, complex problems. We are still in the early stages, patiently waiting for the technology to mature beyond the laboratory. The promise of quantum is staggering, from new medicines to unbreakable logistics, but we must first conquer the fundamental engineering hurdles while simultaneously preparing for the security risks that its power will inevitably bring.